Greetings everyone. So today we are going to discuss about the Raoult's law. So Raoult's basically he was a French chemist, F.M. Raoult, who purposed his law in 1887, which was in relation with you know providing a correlation between the vapor pressure of a solution and its correlation with the mole fraction of solute and solvent. So what he actually said was that first and foremost, Raoult's law, as previously told, it basically gives us the best criterion to classify ideal and non-ideal solutions. We have ideal solutions such as benzene, toluene, benzene. We have examples of bromobenzene, chromobenzene, and after that we have examples of benzene, ether, which are basically the ideal solutions. But on the other side, we have some non-ideal solutions as well, such as HCl and water. So all of these solutions are classified on the basis of the following of Raoult's law. Whether if the solution, if these solutions follow the Raoult's law, these are considered as ideal, and if not, these are non-ideal or real solutions. Coming to the point, what his statement was is that he said that the vapor pressure of a non-volatile solute. Vapor pressure of a solution with a non-volatile solute is directly proportional to the mole fraction of the solvent, such that if we were supposed to write this equation, we can simply write, we can consider x1 as mole fraction of the solute, x2 as a mole fraction of the solvent. Let's suppose it's only for example. And here we are having the vapor pressure of the entire solution, which is represented by P, right? So we can say that P is directly proportional to the concentration. Oh, sorry, yes, we can call it concentration because mole fraction is a unit of concentration. Mole fraction is directly proportional to the concentrate molar mole fraction mole sorry vapor pressure of the entire solution is directly proportional to the mole fraction or the concentration of the solvent. So this is how we are going to write it, but if we remove the proportionality sign, we'll add a constant, and constant in this case would be the vapor pressure of the pure solvent, vapor pressure of the pure solvent, and for that we are going to represent it by P naught. So P naught x2 would be the condition over here, right? So this is what is signified by the Raoult's law. Now if we come to manipulate it, we know that x1 plus x2 mole fraction of all components of a solution is equal to 1, or unity, due to which we can say that x1 plus x2 is equals to 1. So if we want to manipulate x2, we can say that x2 is equals to 1 minus x1. This can be the possibility. So what we are going to do is to multiply or put the value of x2 over here, such that P is equals to P naught 1 minus x1, 1 minus x1, right? And here when we are going to manipulate it, we can say that here we have P is equals to P naught into 1 P naught, and then P naught into x1, P naught x1, right? This is how we do it, P naught x1. And after that, uh yes, so when we are going to move P naught on the other hand side, it will become as P naught P minus P naught is equals to minus P naught x1. Now here, let me just write it a bit clearly. It is basically a P. Oops. Let me just write it a bit clearly over here. It is P minus P naught is equals to minus P naught x1. Now in this case, we can see that here there is a minus sign. If we want to remove that minus sign, we can directly change the sign of the other side of the equation, such that instead of writing P minus P naught, we can write P naught minus P. So writing P naught minus P is equals to P naught x1, right? And here P naught minus P would be considered as the lowering in vapor pressure, because there's a condition given that whenever, according to Raoult's law, that whenever we have the mole fraction of the solute increased, there would be increase in the lowering of vapor pressure. Now you might be wondering that why is there a lowering of vapor pressure in case of Raoult's law. So let us discuss that as well. Let's suppose if we have a pure solvent, pure water, let's suppose. And pure water is having all of its surface particle, all of its surface area is covered with a surface particle of molecules of water, right? But when it comes to the solution of NaCl with water, in this case, some of the surface, much of the surface area is covered by water, but some of the surface area is also covered by NaCl, such that surface particles are also considered to be NaCl as well as water molecules, which means here there are some molecules of NaCl and some molecules of water are there, right? Now some molecules of water and some molecules of NaCl being there will now cause to decrease the surface area of water molecules, which means less water molecules are present on the surface area due to the presence of water NaCl molecules over there. The surface area of the water molecules will be decreased because the water molecules are now less in number on the surface, as a result of which it will lead to less rate of evaporation. As a result of less evaporation occurring, there would be less condensation occurring. As a result of less condensation, there would be less vapor pressure, due to which the vapor pressure being lowered down would be less than the vapor pressure of the pure component or the pure solvent or water. As a result of which, there is always a lowering in vapor pressure whenever the solute is combined with a volatile solvent. Whenever a non-volatile solid is combined with a volatile solvent, it causes to give us the solution which is having lower vapor pressure than the pure solvent. So in this case, this is what we are going to conclude, that here there is lowering of vapor pressure. It is denoted by lowering of vapor pressure. Delta P is equals to P naught x1 is equals to P naught x1. Now in this case, we can say that lowering in vapor pressure is directly proportional after removing. So since we have, P naught is what? It is a constant. So we need to take it as a constant, and when we are going to take it as a constant and take these values, we can say that lowering in vapor pressure is directly proportional to what we call as mole fraction of the solute. So this is how we concluded, right? Uh, all right, after that we are having the condition again. We are going to again describe that condition, rewrite it. So here p naught is being multiplied with x1. Now on the other hand side, it would be divided by delta p, due to which it will become delta p upon p naught is equals to x1. Delta p upon p naught is equals to x1. Now delta p upon p naught is what we can call as the relative lowering in vapor pressure. Relative lowering in vapor pressure um, is considered as the mole fraction of the solute, which means we can say that according to the Raoult's law, relative lowering in vapor pressure is equal to the mole fraction of the solute. And we can also prove it. Later on, we'll be proving it as well. And on the other hand side, if we talk about, what do we call it? The relative lowering in vapor pressure is dependent on temperature, because if temperature is increased, rate of vapor pressure is ultimately increased, due to which lowering in vapor pressure is ultimately decreased. But when it comes to relative lowering in vapor pressure, it is independent of temperature, but it is dependent on the concentration of solute, because concentration of solute is involved in lowering in vapor pressure. And apart from that, it is also constant when equimolecular proportions of the same solute is utilized in the same amount of solvent. If there is equimolecular concentration of different solutes in the same amount of solvent, so at that moment this equimolecular concentration of the solute in the same amount of solvent will be, so equimolecular concentration of solute in the same amount of solvent, equimolecular concentration of solute in the same amount of solvent will have the value of relative lowering in vapor pressure as constant, because relative lowering in vapor pressure only involves the vapor pressure of the entire solvent as well as the vapor pressure of the solution. So due to this, we can say that relative lowering in vapor pressure is only dependent on the concentration of solute. These are some statements presented by Raoult's law, but here we are going to discuss something else as well. That here Raoult's law also describes us that whenever there are two solutions which are volatile, both two miscible liquids are there, two volatile miscible liquids are mixed with each other, then at that moment, these two volatile liquids being mixed with each other will now cause to produce We'll have now these, let's suppose two volatile liquids are there. Two volatile liquids are there. Um, Two volatile liquids are there, right? So these two volatile liquids within these solutions, these volatile liquids, when these are mixed and miscible with each other, it causes to have a partial pressure, such that if we consider the vapor pressure of a solvent A, let's suppose, which is represented by black particles, which is considered as having vapor pressure PA. Now this vapor pressure PA can also be considered in terms of partial pressure, because we can say that this vapor pressure plus the vapor pressure of component B would be equal to the total pressure of the solution. In a sense, we can say it, because vapor pressure of A plus vapor pressure of B will be equal to the total pressure of the solution exerted on the walls of the solution, due to which we can say this entire equation can be considered in this condition, due to which we can say that partial pressure here would be considered as vapor pressure, due to which we can say that here we have the vapor pressure, partial pressure, sorry, equal to P naught A. P naught A represents what? It represents the vapor pressure of the component A as a pure solute, as a pure liquid, sorry, and its mole fraction. Likewise, if we talk about Pb, we are having its value according to the Raoult's law as P naught B, vapor pressure of the pure solvent, into xv, right? And if you are supposed to manipulate it further, we can say that here p, now putting the values over here, we can simply write that as p naught a xa as the value of pa, and p naught b xb as a value of pb, xb as a value of pb combined together is equals to the total pressure. Now we know that value of xa plus xb is equals to 1. So at that moment, if this is a binary solution, then we can consider xa plus xb equal to 1. And if we want to consider the value of, let's suppose, xb, so xb is equals to 1 minus xa, 1 minus xa. So in this case, we can put the value of xb into the equation, due to which it will become p naught a xa plus p naught b 1 minus xa, 1 minus xa. After that, p naught a xa plus p naught b after further manipulation would be equal to p naught a xa plus p naught b into 1 is equals to p naught b. After that, p naught b into xa is equals to minus p naught b xa, minus p naught b xa. Now when we are going to take the common answer, let's suppose, let's see what is common over here. We are having p naught b as the common and xa as the common, so we can take p naught b, p naught b plus xa as a common out of both of these terms, and the rest of the equation obtained would be equal to pa pa minus pb, pa minus pb. So this is how the entire equation can be written. and this is how we are going to do it. Apart from that, this is what we considered in the case of total pressure exerted, I mean calculated in terms of Raoult's law. Apart from which, we are having a graph which is considered when explaining the Raoult's law over here. That here we are having a graph which basically showcases us the relationship of the Raoult's law, such that here we are having two components, component A and B. A can be considered having low boiling point, B can be considered having high boiling point. B having high boiling point, A having low boiling point. Since A is having low boiling point, it is supposed to have a higher vapor pressure at constant atmospheric pressure, such that at the constant atmospheric pressure there would be a higher vapor pressure of the one which is having the lower boiling point, due to which we can say that it is having lower vapor pressure. Low vapor pressure is lower, and here the vapor pressure is higher. Sorry, here the vapor pressure is higher in XA because there is lower boiling point, and on the other side in XB their vapor pressure is lower due to high boiling point, right? And as there is high vapor pressure in XA, it indicates that XA basically has more volatility as compared to XB, due to which XA would be considered as more volatile, and XB would be considered as less volatile, due to which we can say that in a sense XB being less volatile can be written as the solute, and XA being more volatile can be written as the solvent. So accordingly, when we are going to draw the graph of both of these, we can consider a graph in which we have the mole fraction or concentrations on the x-axis, while the vapor pressure on the y-axis. This is a graph over which we can see the total pressure. This is what we consider as the total vapor pressure of the entire solution. This is what we consider as the total vapor pressure of the entire solution. And here, as you can see, as the concentration of the solute as the concentration of the solute is being increased, concentration of the solute, which is XB, as the concentration of the solute is being increased, the vapor pressure is gradually being decreased. Vapor pressure is gradually being decreased. Likewise, if the concentration of the solvent XA is increased, the vapor pressure is increased. The vapor pressure is increased due to of the entire solution is increased as a result of increase in the concentration of the solvent, right? And lowering in vapor pressure is directly proportional to XB, because XB is the solute, due to which lowering in vapor pressure occurs when the amount or concentration of the solute XB is being increased, as a result of which, as the concentration of the amount of the solute is being increased of XB, it causes a lowering in vapor pressure which is quite higher, as a result of which we can say that lowering in vapor pressure here is directly proportional to the mole fraction of solute, and vapor pressure is directly proportional to the mole fraction of the solvent, which gives us the conclusion that this graph obeys the Raoult's law. Now all of those solutions which obey this graph and the Raoult's law would be considered as ideal, and those which would be showing a deviation from this straight line graph, those which be showing a deviation from the straight line graph, either positive deviation which would be above the straight line, or negative deviation below the straight line, would be considered as non-ideal solutions or real solutions. Another name for these solutions is non-zeotropic solutions, non-zeotropic solutions, or azeotropic solutions, while those solutions which would be obeying also would be ideal solutions or zeotropic solutions, right? And here, as you can see, there are certain points of consideration, that here if we have PB, if we have partial mole fraction of B increasing, mole fraction of the solvent is increasing, so vapor pressure of the mole fraction of the solvent is increasing, so at that moment the vapor pressure of the solvent is also increasing. If the mole pressure of the solvent is increasing, vapor pressure of the solvent is also increasing. If the mole fraction of the solute is increasing, then the vapor pressure of the solute is increasing. But what we can really see over here is that if the vapor pressure, alongside the increase in the vapor pressure, there is an increase in the vapor pressure of the entire individual solvent as well, which means that here the vapor pressure of the entire solution can be considered dependent on the vapor pressure of the solvent, or in other words, we can also say that vapor pressure of the solvent and vapor pressure of the solution show a positive straight line, while vapor pressure of the solution and the vapor pressure of the solute show an opposite straight line within the graph. So this can be the consideration as well. Now when it comes to those solutions which do not show any those solutions which show deviation, so we need to first understand two terminologies which include zeotropic and azeotropic. Zeotropic solutions are those solutions which, when filtered, we know that in ideal solutions we are having solute solute, solvent solvent, and solute solvent interaction all equal to each other, due to which the polarizability. And why is that so? This is because of the polarizability being same, size being same, shape being same, overall structure of those molecules of or particles of the solute and solvent being similar, as a result of which the particles will be having similar forces of attraction, due to which the molecules will be in a fixed composition throughout the mixture. As a result of molecules being in fixed composition throughout the mixture, will now tend to remain without stronger intermolecular forces of interaction, due to which, because of absence of polarizability, as a result of which the molecules obtained in this case would be molecules obtained in this case 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 can be separated by distal friction distal fractional distillation sorry fractional distillation process. Why is that so? Reason behind it is that we are having intermolecular force of interaction quite similar, as a result of which, if we are supposed to separate it through the process of fractional distillation, due to the fixed composition present throughout the mixture, we are able to easily bring about uh, a change in the composition of the solution by separating the solute and solvent, as a result of which the distillation fractional distillation is possible, um, which causes fractional distillation is possible with a change in concentration with a concentration change in concentration of the solution. Fraction distillation is possible with a change in concentration of the solute and solvent, as a result of which this process can lead to those solutions which can undergo fractional distillation with a change in their concentration, which are considered to be as zeotropic mixtures. And these zeotropic mixtures are having some of their vapor pressure of solute and solvent equal to vapor pressure of solution. But when it comes to those solutions which are azeotropic or non-ideal, these are those solutions which are having a polarizability within their intermolecular forces of interaction, due to which solute solvent interaction, solute solvent, solute solute solvent solvent, and solute solvent interaction being unequal have polarizability, due to which there is higher polarizability, high intermolecular forces of attraction, due to which they tend to maintain a greater bonding capability. Now, why is that so? This is because of the size, shape, and polarizability. I mean, the variation in the size, shape, and structure of the solute and solvent particles, as a result of which it causes to give us an entirely solute and solvent particles, as a result of which it causes to give us an entirely different entirely stronger structure with polarizability, due to which, when we are supposed to separate it through a fractional distillation process, this uh, causes to give us no change in concentration of the solute and solvent through the fractional distillation process, if it is uh, occurs in case of fractional distillation, right? So this is something which occurs in those solutions which are considered as azeotropic or non-ideal or real solutions, in which the fractional distillation does not cause any change in concentration. Now, if we talk about those non-ideal solutions or azeotropic solutions, there are two conditions: either those solutions which are with positive deviation, or those solutions which are with negative deviation. For those solutions which are positive azeotropes basically have their vapor pressure increased. They have higher vapor pressure than the ideal solution. They have higher vapor pressure and lower boiling point, such that they have higher vapor pressure than vapor pressure of the pure components, and lower boiling point as compared to the boiling point of the pure components. Likewise, if we talk about if we talk about vapor pressure of those azeotrophs which are having negative deviation, these would be considered as negative azeotrophs, and these negative azeotrophs will have vapor pressure which would be which will have be a vapor pressure which would be less than the vapor pressure of the pure components, and will have boiling point which would be greater than the boiling point of the pure components. Example of positive deviating azeotrophs involves positive deviating azeotrophs involves examples of um, alcohol, ethyl alcohol, and water, where ethyl alcohol is found 95.5%, water 4.5%, where the boiling point becomes 78.1 centigrade, such that the boiling point here is less than the boiling point of the pure components, which includes water having boiling point at 100 centigrade and ethyl alcohol having boiling point at 78.5 centigrade, due to which we can say that boiling point is lower than the boiling point of the pure components and vapor pressure is higher than the vapor pressure of the pure components. Likewise, if we talk about negative deviation, we have HCl. HCl in such a manner that if we are having 20.24% HCl concentration, 20.24% of HCl concentration with water, we are having the boiling point greater than the boiling point of the pure components, and vapor pressure less than the vapor pressure of the pure components, due to which we can say that boiling point would be greater than the boiling point of the pure component, which is equal to 110 centigrade. Since water is having boiling point as 100 centigrade and HCl is also having nearest to it something like 108 something, something less than that, so here 110 centigrade is a boiling point of HCl 22.4% acid with water. So in this case, these are some negative deviation and some concepts, apart from which we are having colligative properties, which I want to discuss over here. That colligative properties are those properties which are dependent on the number of particles of solute and solvent. If we take, let's suppose, zero point 0.1 mole of sugar, zero point 0.1 mole of glucose, zero point 0.1 mole, zero point 0.1 mole of glucose, zero point 0.1 mole of sucrose, and zero point 0.1 mole of urea. So in that case, if we take all of these solutions and dissolve them in 1 kilogram of water in order to produce 1 molar solution of all of these three, 1 molar solution, sorry, it would be a zero point 0.1 molar solution of all of these three, then at that moment, these zero point 0.1 molar solution of all of these three should have the mass of urea, should it should show us that since sucrose is having the highest mass, sucrose should its mass is basically 342 gram, right? So since sucrose is having the highest mass, sucrose should have the highest vapor pressure. But if we consider taking zero point 0.1 molar solution of all of these three, we find in actual that the vapor pressure of all of these three components is same. Reason behind it is that the number of particles of all of these three components are same, which is 6.02 into 10 to the power 23 divided by 10, which means 6.02 into 10 to the power 22 particles are there of all of these molecules. 6.2 into 10 to the power 22 molecules of all of these components are there. due to which the vapor pressure is same in all of these if we consider. So in that case we can say that this is a property which is dependent on the collective number of particles of molecules, collective number of particles of molecules, as a result of which uh, we can say that these are dependent on the collective number of particles of molecules of these compounds, due to which these properties, which are only dependent on the number of particles rather than the structure or the arrangement of particles, is known as colligative property. Among that we have lowering of vapor pressure, which I have here discussed. In the next video we are going to discuss about its derivation. Just about the hopefully we meet again in the